When we're dealing with recurrence relations, the method of iteration we know is extremely handy in helping us solve recurrence relations. And let's just recall momentarily what that means. So I have some recurrence relation that says that the next term is maybe 2 times the previous term plus 1. Okay? Now this is really telling me that if you give me the starting value, if you give me A0, then I can get A1 by taking, okay, let's say A0 is 5. A1, if this is a 1, this subscript is 1 less than the subscript n. So 2 times A0 will be 10 plus 1, which is 11. So that gives me A1 is 11. Now if I want A2, I have to take 2 times A1, which will be 22, plus 1 will be 23. The problem, or the general issue with this, is that if I wanted to get to, say, A100, I would have to do 99 iterations of this process. Actually, 100 iterations. I'd have to go A1, A2, A3, all the way up until I get to A100. And this is a costly process because it requires a lot of computation to get there. The question that we aim to address by solving a recurrence relation is to say, what would the function look like that just allows me to find any value of a sub n strictly based upon a sub 0? So instead of having all these little arrows that kind of hop from one value to the next, what we want is we want some sort of function that will allow us jump directly to A100. But based upon this just gives us the recursive relationship between the next and the previous value. So we've learned to solve this type of recurrence relation with the method of iteration. Now, there are some difference equations or recurrence relations that are frequent enough, are common enough to where we might ask ourselves, is there a faster way to do this? Do we need to reinvent the wheel and use method of iteration each and every time? Well, we know from our math experiences in general that the answer is no. A lot of times we can find sort of closed form solutions or some sort of package that really allows us to quickly produce this type of relationship. So we've been focusing on one, which is called the first order linear difference equation. And we're not going to get into what all this means here. But the point is that this is first order in the sense that the next value only depends on the most previous value, that it depends on just the last value. Linear, there's no exponentiation of our, for example, if we had Sn minus 1 squared, that would be a nonlinear difference equation. And constant coefficients just means that these values of a and b, this coefficient of the previous term and this value that's getting added to that multiple of the previous term, that those two values are going to be constants. They don't always have to be, but when they are, it turns out there's a nice way that we could study this relationship. So for example, you can see that this one up here, a sub n equals 2 times a sub n minus 1 plus 1, or the next term is twice the previous term plus 1, has this general form. The next term is some multiple of the previous term plus some constant. Let's see if we can just leave a and b in there instead of, for example, 2 and 1, and see if we could find a solution in terms of a and b. So we would still use method of iteration here. We would say that, all right, S1 will be a times S0 plus b. And now we would iterate to the next term. We'd say, well, S2 equals a times S1 plus b. Now, wait a minute, S1 is equal to this thing here. So I'm going to replace S1 with a times S0 plus b plus b. And you see that S2 doesn't depend on S1 anymore. It now depends explicitly on S0. Well, this becomes, if we distribute a times a S naught, will be a squared times S naught plus a times b, and then plus our final term b here. Now, S3 will follow a similar procedure. It will be a times S2 plus b. It's a times the previous plus b. But S2 is now this whole expression here. So now I could replace S2 with a squared times S naught plus ab plus b, and then this additional term plus b here. And if I distribute that to the three terms I have in the parentheses, I get a cubed times S naught plus a times b, which is a squared times b, plus a times b, and then plus this final b. Now I suspect a pattern already. I see that the subscript is the power on the value of a that multiplies our initial condition S naught. And then I have in decreasing powers a squared, a to the first, and by the way, even though that plus b term doesn't have an a in front of it, it has a coefficient of 1, there's no harm in putting an a to the 0 there. So a to the 0 is 1, as long as a is not 0, of course. That would not be a very interesting recurrence relation. And so now I'm going to make the general claim that it appears that S sub n will be a to the n times S0. All of these terms have a times b in it, but it looks like it will be in decreasing order. It'll be a to the n minus 1 times b, so a to the power that's 1 less than this power here, plus a to the n minus 2 times b, and I don't know how many of these terms there are going to be, other than there's going to be n plus 1 total terms, because I'm going to have a to the first times b plus a to the 0 times b. Okay, well, from these terms here, since they're all very similar, I noticed that I could factor out a b. So a times n, a to the n times S naught, I know what a is, I know what n is, well, in any situation I will know what they are, I'll know what the initial condition is, but this is what's going to cause me the headache here, is I have to do a lot of addition still. And the goal is to compact that into something that doesn't require as much arithmetic. So I'm going to factor that b out. I have a to the n minus 1 plus a to the n minus 2 plus all the way down to here I factored out a b. And in this last term I factor out a b. Now I'm going to go ahead and write a to the 0 as 1, because now this looks like an arithmetic series, and what we know is that if we add 1 plus x squared all the way up to x to the n, then this is going to be x to the n plus 1 minus 1 over x minus 1. That's what we know from an arithmetic series, that it converges, that it'll become this value, that it always is this value. Now, the relationship here is that x is our base, and that whatever the power on the last term in our sum is, notice that this x in the numerator is going to have a power that is 1 bigger than our largest power of that base. So in our situation here, notice that we have 1 plus a to the first plus a squared plus all the way up to a to the n minus 1. which means that this will, when we write this expression here, that whole thing is going to be a to the largest power plus 1. So in our case, n minus 1 is the largest power, so add 1 to that. Well, n minus 1 plus 1, n minus 1 plus 1 is going to be just n. N minus 1 plus 1 is just n. Minus 1 over a minus 1. So all I've done is, just like here, the sum of all of those terms is equal to this thing. The sum of all of these terms is equal to this thing. And now I have a nice compact expression. This is a to the n times s0 plus b times this whole thing here. And that is my final expression for s sub n. Now, notice how now we have everything in terms of a and b. So whatever we're given up here, we don't need to go through this entire process anymore. We can just say, well, to find the nth term, all I have to do is plug in my a, my s naught, my b, and my n. Now we can just do a little bit of cleanup work on this, and we can say that this is if I do some distribution, this is going to equal, let's see, a to the n times s naught. Now I'll just distribute the b into the numerator, so I'll make this plus b over a minus 1 times a to the n. Okay, so that's just multiplication of that term. And I'll distribute it here as well. So I'll have minus b over a minus 1. And so basically, since this is a fraction, just like we would write 3 plus 2 over 7 is the same thing as 3 over 7 plus 2 over 7. I've just broken these up into two terms. Now I am going to go ahead and from these two terms factor out, and again, we're pretty much done at this point, but to get it into a prettier, more compact version, I'm going to factor out an a to the n from these two terms here, so that'll just leave me with s naught plus, now I'm going to, because I don't like this messy b over a minus 1, I'm just going to say plus c. And then I will have minus c. So I'm just going to call c, I'm going to let that take on the value b over a minus 1. And again, that's not something that we have to do. It just makes this look a little bit prettier. So that means that our expression for s sub n equals this expression here. Now there's one little problem, and that one little problem is, well, what if a is 1? If a is 1, that kind of knocks things out of the water here, because we'll have division by 0. So this is for when a is not equal to 1. This formula will work. So what that means is that if you have a situation that is not covered by your solution, you have to consider what that would look like if a was 1 and how that would change the answer. So let's actually just go ahead and plug in 1 for a back into our original expression and see how that's going to change our solution, so that in situations where a is 1, where, for instance, if our next term is just our previous term plus 2, for instance, then that's not covered by what we've just deduced here into this box. Let's go ahead and take a look at what that would look like if we were to have a value of a equals 1. Now, if a equals 1, then the only thing that we're going to change is we're just going to say 1 times s0 plus b. So we're going to write a general equation here for any constant b, but where a is equal to 1. So in a way, this is a little bit even easier because, this is Sn minus 1 here. So to write S1, well, that'll be 1 times S0 plus b. S2 will equal S1 plus b. But wait a minute, S1 is equal to S0 plus b. Now, because because my coefficient out here is a 1, notice that I don't have to distribute that 1 in because it's not going to change what's in that parenthetical expression. So what I really have here is S0 plus b, which is S0 plus 2b. Now let's look at S3 before we're ready to make a conclusion. That's going to be S2 plus b. Well, S2, we're going to substitute in this expression. So we have S0 plus 2b plus b. And that's just going to be S0 plus 3b. So because we're just adding a constant at each iteration, and we're not actually multiplying the previous term by anything but 1, we're really just adding another layer of b each iteration. So I think it's fair to say that Sn will be the initial value plus n multiples of b. So if we go 100 terms out, we're going to have to add b 100 times to the initial value. And so this is our solution right here when a equals 1. So we have one of two possible situations, and we're going to go ahead and summarize that now. The beauty is that we don't have to derive this again. We've just derived the general solution. And so next time when we encounter a recurrence relation of this form, we can just jump straight to the solution. S sub n, when S sub n equals some constant times the previous value plus some constant, where a and b are real numbers, the general solution is this first one that we derived. If a is not 1, it is equal to S0 plus n times b if a is equal to 1. And then we called this value of c just only for the purposes of making that expression here look cleaner. We've just replaced b over a minus 1 with c. Now be cautious, the plus c and the minus c here don't cancel out because this c inside the parentheses gets multiplied by the a to the n. Well, now that we have our general solution, let's just see how easy it is to tackle a problem something like this. A lumber company owns 7,000 birch trees. Each year the company plans to harvest 12% of its trees and plant 600 new ones. All right, let's sort of think about what happens over the first couple of years. Let's call the number of trees T and the number of years N. So T sub n is equal to the number of trees after n years. So let's see how this would work. When n is 0, we know there are 7,000 birch trees. Now 1 year later, we know that we're going to harvest 12% of these 7,000. But we want to know not how many do we get, but how many do we leave behind. Well, if we're harvesting 12% of its trees, that means we're only going to have 88% of the 7,000 left. Again, 12% get removed. We're asking how many trees will there be in our tree forest. And we're also going to plant 600 new ones. Well, I can do the math on that. I can see that that's 0.88 times 7,000 plus 600 comes out to 6,760 trees. All right, well, after at time 2, there will be 88% of the 6,760 that we now have in the forest. So remember, we're going to harvest 12%, we're going to leave behind 88%, and then we're going to plant 600 new ones. So 88% of 6,760 plus 600 shows me that the number of trees is actually dwindling. We're losing trees because we're harvesting more than we're planting. And in this fashion, we could say that after n years, we're going to be taking 88% of t sub n minus 1. That's how many trees there were in the previous year. And then we're going to add 600. So now we have our recursive relation, which is often half the battle. The number of trees 1 year later will be 88% of the trees that we had at the beginning of the year plus the 600 new ones that we plant. Now, at this point, we would normally have to go through the method of iteration to solve this, but now that we have our lovely solution here, we can just focus on identifying our A and our B. Now, our A and our B are the 0.88, that's our multiplier on our previous. Our 600 is the constant that's being added each year. We know that T initial is 7,000, and we have everything that we need. Now, since A is not equal to 1, we know that we're going to use this first general solution. So Tn will equal A to the n, so 0.88 to the n, times the initial, S initial, or T initial, 7,000, plus C. Now, wait a minute. I'm going to go ahead and just calculate C over here. C is equal to B over A minus 1, which will come out to 600 divided by negative 0.12. That comes out to negative 5,000. So C is equal to negative 5,000. So I'll have 7,000 plus negative 5,000, and then minus negative 5,000. Watch the sign here, because we have minus C. C is a negative number, so minus a negative. And so our final expression is T sub n equals 2,000 times 0.88 to the n plus 5,000. Just as simple as that. That took us basically 2 lines to find that general solution. At this point, we can just verify that, for example, if I tried T1, that would be 2,000 times 0.88 to the first power plus 5,000. So I get 6,760, so I see that my formula works. If I do 0.88 squared instead of 0.88 to the first, I get 6,548.8. And so this general solution actually does work. Now, I can focus on answering some real-world questions. So now I could say that T of 10 is going to be 2,000 times 0.88 to the 10th plus 5,000. So in my calculator, I can just put in the previous line, and I get about 5,557.002, so about 5,557 trees. Now, what's going to happen in the long run? Well, in the long run, notice first of all one interesting aspect, that we are losing trees from 1 year to the next, but we're only removing 12% of what is there. And at some point, at first we lose about 240 trees, but then we lose only about 211 trees. So the reduction, 240, here we have about 211. The amount that we're removing from that forest becomes less and less, And the reason for that is because we're always only taking away 12% of what remains. So eventually, 12% of some value will be exactly what we're adding in that given year. So the point is, we're not going to actually deplete the forest. I'm going to do a limit observation here. I'm going to say what happens as n gets really, really large to t sub n. And without doing any real calculus here, I'm just going to look at each term and say, what happens to that term as n gets large? Well, notice here in this first one that 2000 is always that coefficient. But here I'm taking a number that's between 0 and 1 and raising it to a power. So if I take 0.88 to the 10th, for example, that number is 0.28. That number is getting smaller. But if I take 0.88, say, to the 100th power, 0.88 to the 100th power is approximately 0. So as n becomes really large, this guy here approaches 0, and 2000 times 0 is still 0. So that first term gets closer to 0, but the second term gets closer to 5,000. And so I can say that over the long haul, I would expect that tree population in the forest to stabilize at about 5,000 trees. Now, let's go ahead and just study this, look at this relation in technology and see that this does actually hold true. So here I've just plotted t of n, could use x instead of n. T of n equals 2000 times 0.88 to the n plus 5,000. There's our initial condition satisfied, times 0, 7,000 birch trees. So along this axis we have the number of birch trees. Along the horizontal axis we have the number of years. And we see that the number of trees is dropping. We can see at time 1 year there are those 6,760 birch trees. By the way, even though this graph is continuous, we're not really dealing with fractions of years here. So it only makes sense to look at these at 1 year increments. But we are getting a smooth curve that gets plotted because this is being thought of as a continuous function by our graphing utility. And I can see that as the years pass, the decay rate, we have the number of birch trees is decreasing at a slower and slower rate until we can see that it flattens out right around 5,000. You can see that we're at 5,017 and really starting to taper off. And I can see that way out here, after 65, 70 years of this type of harvesting, we get closer and closer to 2,000 trees. Great. So that means that we start to approach 5,000 trees. Now, this is one type of recurrence relation. This is where we'll stop with this particular type. But up next, we're going to consider the situation where we have what's called a second order equation, and that is one similar to the Fibonacci sequence, where the next term is the sum of the previous two terms. And in this case, we have the input of two previous values, two inputs, to get one output. And we want to understand how we could solve something like this, because it's not very easy to do by the method of iteration.